Alright, so here we have a arm holding up a mass, and we are wondering what force the bicep has to put on the lower arm in order to hold this mass up. This makes 90 degrees. The upper arm is vertical, the lower arm is horizontal. We know a few things. We know the mass of the weight here, of the thing you're holding up. We know the mass of the lower arm. We know where the center of mass of the lower arm is. We know that distance from here, like so. We also know the distance all the way to the mass. Let's see. And we also know the distance from the actual bone joint to where the bicep grabs on. There is a little bit of distance there. We will find that you wouldn't be able to lift things if there wasn't. Alright. So, I've got my picture listed up there with the dimensions. Now let's do a free body diagram. Separately, I suppose. I don't really need much there. So the interesting thing is probably the lower arm. It's got the mass sitting on it. That's my new mass, the new look. mg, right? It's got its own mass, little mg, right? And apparently, so there's where it attaches to the upper arm. And we've also got this force from the bicep pulling up. And whenever we've got a problem that has some sort of a hinge in it, shall we call this a hinge? It's good practice to just put an X and Y force there. Okay, so what shall I call them? I'll call them R for reaction. Rx, let's see, Ry, and Rx forces. Those might be 0, alright? So, for example, I don't know if there'll be any force in the X direction there, but I usually just put them in, and the math will show us that it's 0 later. Alright, so the free body diagram is all set. It's got all the forces in it. And I am looking for F, right? I'm looking for the force the bicep has to exert on the lower arm in order to hold this mass up. So, yeah, I might think some of the forces, right? That's what we usually do. But if I was to do the sum of the forces in the y direction, let's try it, equals mass times acceleration. But it's 0 in this case. We're holding it steady, right? I would get, what have I got? Well, let's say that up is the positive direction, positive y direction. That would mean I'm getting Ry plus F minus mg minus big M g. And I've got 2 unknowns in this equation, right? So I'm not going to be able to do it. Now, the x equation is not going to give me much. Sum of the forces in the x direction, mass times acceleration in the x direction, is 0 and is equal to Rx. That's the only force that I wrote in the x direction. Yeah, so in fact there is no force at the joint in the r direction, but clearly the x equation didn't help much. I'm looking for F. So, well, all I have left is the torques. The sum of the torques, a good hint to know to use the sum of the torques, is that this is a problem where we have a hinge, a pivot point, an axis, whatever you like. And so I'm going to sum the torques about the elbow joint. That should be I alpha, but also 0. Now that means I'll need to define my rotational axis. I'm going to say that that way is positive, I guess. Alright, so if that way is positive, the torques due to gravity are positive, and the other 2 forces are causing negative torque. So let's write in just a symbol representing each torque. So it'll be the torque due to the force. That's going to be in the that's going to be in the negative direction there, plus the torque due to the little mass plus the torque due to the big mass. We've got Well, I don't know about these. I'll put them in for a second. The torque due to that Rx and the torque due to that Ry. Okay, so let's put in these knowing the definition of torque in general is F times R times the sine of the angle between them, R being the distance from the force to the pivot point. So we have some distances like that here. Now we're going to go ahead and use this definition for our forces here. So 0 equals, okay, negative F, torque due to F. That's going to be F times, the distance is d3 to the pivot point, times the sine of the angle between them. So for F, that's 90 degrees. In fact, looking ahead here, most of these are 90 degrees. All right, so the sine of 90 is 1. So I'm just going to leave the sine of 90 off of this equation because it's just going to be a 1. All right, so that's negative F d3 plus the torque due to the little mass, which is the force is mg, and the distance is d2, plus the torque due to the big mass, the force is big mg, the distance is d1. All right, and now if I think about the torque due to these x and y reaction forces, what's the distance from these forces to the pivot point? It's 0. They're at the pivot point. This is the best thing about summing the torques. You get to pick where you want to place your pivot point. Now in this case it was obvious we should use that. But the great thing about it is that it essentially gets rid of these two numbers, or Ry anyways, that we don't even know, because they're acting at the pivot point. The R in their torque equation is 0, so they are giving 0 torque about the elbow. Okay, so then in that case, that's just to remind ourselves, that's plus 0 for each of those. And so looking to solve for F, I can add F over there, divide over D3, and I get F is equal to, I can pull out G here, and so we have solved for the force that your bicep has to exert on your lower arm in order to hold up this mass, big M. Little m is the mass of your arm itself. D2 is the distance to the center of your arm's mass when you're not holding anything. D1 is the distance to your palm, essentially, or wherever you're holding the object. And D3 is that little distance between your bicep and your elbow. Okay, so another question that leads from this that they usually like to ask at this point is, what are the reaction forces in the elbow? In this case, it's the elbow. The reaction forces at the pivot point. So now we can use the sum of the forces. Before, there were too many unknowns. Now I can look back at my sum of the forces equation. I didn't have to do it first, but since I did, I can look at it. I see that, well, the sum of the forces in the x direction is 0, so there is no horizontal reaction force, but I guess that's still an answer. The reaction force in the x direction is 0. Okay. And as for the y direction, well, I've got an equation for it. If I rearrange this equation, I get Ry is equal to, what's it going to be? Gm plus m minus f. And since we just found f, we can plug that expression in, or we can plug the numeric answer we get in right there, and we will have found, most interestingly, I think, the force that the bicep has to exert in order to hold it up. But after having done that, we had enough information to use the sum of the forces in the x and y direction, and we found the reaction forces. Essentially, that'd be the force that the, I don't know the names of these bones, that this bone is exerting on this bone, or the other way around. Alright, so here are our answers.